Ladies and gents, we have come to the pinnacle of the course. Everything leads up to hypothesis testing. Let's take a look at the big flow chart here and take a look at where we're at. So we started with descriptive statistics and then we added in probability. They went together to talk about probability distributions, the binomial and the normal. And from there, we went to inferential statistics. We looked at unit E, which is on sampling distributions and estimation. And parallel to that is unit H, which is hypothesis testing. So this is the end of the road here. This is where we want to get to. Now, there is actually one small unit after that, which is unit R on regression. This is an application unit. It's only a few pages long, and it was added at the request of both the CPA organization as well as MRU, and so we've included that. It'll also be a good jump-off point to Business 307, which follows this. But really, H is the pinnacle of this course, and then we branch out from there in 307. Let's go back to where we were. So, hypothesis testing. Unit H. In this, we're going to take a look at the forms of the hypotheses, levels of significance and errors, the classical approach to conducting hypothesis tests, the p-value approach to conducting hypothesis tests, and then hypothesis tests for the population proportion. I want to tell you that there's actually really nothing new in this particular section. We've got all the formulas that we need. We're just going to formalize the procedures here. So we've actually been doing hypothesis tests here and there in the last couple of units here, especially the last unit in E. We actually saw some hypothesis testing, but it wasn't formalized. So let's formalize this whole thing. I'm going to use an example here from a manufacturer of cigarettes. Why that particular example? It's because they need to meet an industry standard. It's not because I have any great love of cigarettes. In fact, I don't smoke, never have. But the amount of nicotine which is in cigarettes is something which is heavily regulated. So let's take a look at this particular problem here. Manufacturer of a certain brand of cigarettes claims. Whenever you see the word claims, you know that you're talking about a hypothesis test. The big word for confidence intervals is estimate, estimation. But here we're talking about claims. And so it's a claim about a population parameter, in this case, a mean. Claims that each cigarette contains, on average, so a claim about a mean, no more than 1.6 milligrams of nicotine. We're going to call that the hypothesized mu. I'm going to put a little O down here, or it's actually a 0, and it corresponds to this particular little O or 0 down here. And I'll explain that in a bit here. So here's the thing, is that if you're a manufacturer of cigarettes here, every once in a while, you've got a government agency that comes in and tests your cigarettes. Now, they're not going to, of course, destroy your whole production batch for the month and run them through a bunch of chemical analysis. What they do is they take a sample of cigarettes and they pull them apart and they put them through a bunch of chemical analysis and so on like this, and they found out how much nicotine is in each one, and they come up with an average. And the question is that particular average significantly higher than the standard, which in this case is 1.6 milligrams of nicotine? Let me put it to you another way here. I'm just going to draw a little picture like this. So here's possible X bar values, which are sample means. And what we've got here is a standard where mu is equal to 1.6. Now, we get a sample taken, and in this particular case, it's going to be a sample mean, an X bar of 1.7. That's from a sample here of 144 cigarettes, so that's your little n, and then we've got a sample standard deviation, or an S, of 0.5. So the question is that X bar there significantly higher than the 1.6? That wouldn't be a good thing for the manufacturing organization, because it can't have more than 1.6 milligrams of nicotine on average. Now, on average, of course, means that you can have a little bit more or a little bit less, but it should average out to 1.6 milligrams of nicotine per cigarette. The thing to remember about sampling is that there's this thing called sampling error, and that is that, and I've used this example before in class, let's say the average height of college males is 5'10". And so if we were to take a sample of maybe 30 or 50 college males, and they're from across a bunch of different programs, so they're not just business students or not kinesiology students or so on. So they're a good representative sample of the whole population of college males. And if we were to measure their heights, we would end up probably with an average close to 5'10", but it could be a little bit high, it could be a little bit low, it could be really high, it could be really low, just because of sheer dumb luck that we ended up sampling a bunch of really tall guys or a bunch of really short guys. So that can happen. So that's what this particular process is about here, is to recognize that we're not likely, when we take a sample, to get exactly 1.6 milligrams of nicotine, even though that might be the way that the equipment is set up. When we get 1.7, the question is that enough evidence to say that it is significantly higher than 1.6, that we would be concerned enough, if the average is 1.7, that we would say, hey, you're not meeting the standard, you're breaking the law, and slap them with a big fine. When you take a look at 1.7, it doesn't look like it's much different from 1.6. We can take a look at a couple of extremes here. So if I got an average of 1.600001, we would say, well, that's obviously not much different. And so not a big deal, they are meeting the standard. If I got an average of 10, then that's way much, more than 1.6. So we would say it's quite a bit larger. But what about 1.7? The question is, well, what do you think? Fortunately, in Unit E, what we learned about was this distribution of sample means according to the first limit or central limit theorems. And according to the central limit theorem or the first limit theorem, the distribution of sample means is normal. And it's centered on the population mean, in this case of 1.6, which is the standard, and there's a standard deviation, which is sigma over the root of n. And so what we can do is we can take a sample and find out, well, where does 1.7 fall in this distribution? So we can figure out, what is this area here? This area here, in this unit, we're going to call that the p-value. If the p-value is really small, way out in the tail, distribution of all possible sample means. So small p-value indicates significant difference between the X bar value that we got from the sample and the hypothesized value. Usually we use about, say, 5%. That's our level of significance, alpha, which you were introduced to before in Unit E. If, however, that p-value is much larger, which would happen if the 1.7 is fairly close to 1.6, then we would say there's not enough evidence to reject the hypothesis. So that's where we're going. Let's formalize that with a bunch of steps, and we'll add in a little more theory on this, and you'll see how this works out. So the statement that the mean of all cigarettes is 1.6 or less is called the null hypothesis. The null hypothesis is the standard, the status quo. It's the thing that we're actually trying to disprove. So the testing agency comes in, check to see if in fact they actually are. So they have to bring in a lot of evidence to try to disprove that. Now, just a note here is the federal agency isn't necessarily trying to disprove it, that is to say that the company isn't meeting the standard, but it is their job actually to conduct that test. And so in a sense, then from a statistical point of view, they're trying to disprove it to bring enough evidence to say that they're not meeting the standard. Otherwise, they would say there isn't enough evidence to say that they are not meeting the standard. So what we have here then is the null hypothesis is always assumed to be true. And our job in statistics is to try to disprove it by using the sample results. If the null hypothesis is found to be probably incorrect, then we reject the null hypothesis in favor of the alternative hypothesis. So that's what the A stands for, is alternative. And if you take a look at these two together, the HO and the HA, the null hypothesis and the alternative, you can see that they're complementary. So the HO is that mu is less than or equal to 1.6, and then the HA is everything else, that is that mu is greater than 1.6. Notice the term here, probably incorrect. We can't be 100% sure unless we take a census. And so we are just coming up with enough evidence to cause us to reject the null hypothesis in favor of the alternative. One thing that I've got down here is it says, notice that the null hypothesis, the HO, always contains the equal sign. So you always want to write it like this. Mu is less than or equal to 1.6 against the alternative that it's greater than 1.6. That's a convention that we use, but it's also saying that the center of the distribution of sampling means of the hypothesized center of the distribution of sample means is the 1.6, which is the standard. I've got another important note down here, and it says, it's important to note that in reality, a hypothesis test is a two-stage affair. The hypotheses are formed and then the sample is taken. That actually takes some time. Why are we actually doing a particular test? Well, it's to test a hypothesis. So you come up with the hypothesis, and then you come up with what we call the sample design, and we'll talk more about that in Business 307. And then from that, we go and we take a sample, we come up with the test statistic, which is the X bar value, and then we make our conclusion. There's a time lag there. And so it's really important that the 1.7, which is a sample mean, doesn't in any way affect the formulation of the hypotheses, because in reality, we haven't even taken the sample yet. The hypotheses can take three different forms. So when you see something worded like this, the manufacturer claims at most 1.6 milligrams of nicotine, then it means mu is less than or equal to 1.6. The opposite would be at least, which would be greater than or equal to 1.6. Sometimes it's equal to 1.6. They don't usually say exactly 1.6, but we would write that like so. And that means that either a very high sample mean or a very low sample mean would cause us to reject the null hypothesis in favor of the alternative. We'll see an example of that a little bit later. Now, to help you understand this a little more, we want to think of this as being a court case. Oh, wait a minute. Before I get there, this is really, really an important statement here. I want you to put some stars around this. I want you to put some NBs And I want you to put some arrows here because this is really important. Let's put a green box around it because it's really important. You always want to come back to this. The HO is always represents the traditional claim, the historical claim, the status quo, or in cases where no studies have been done before, the only claim being made. HA represents the new claim. So we'll see that a little bit later in some examples, but I want you to remember that statement and we'll keep coming back to that. Okay, let's take a look at a hypothesis test in terms of a court case. So in a court case, what you have here is that the defendant is innocent until proven guilty. The equivalent in a hypothesis test is that HO is assumed to be true on the onset. And then you have to bring in the evidence. So in a court case, the prosecutor brings in evidence trying to prove the guilt of the party, of the defendant. In hypothesis testing, a sample is taken and sample statistics are calculated. Is there enough evidence to reject the null hypothesis? In the court case, the defendant is found guilty beyond a reasonable shadow of doubt, and therefore there's a conviction. If the sample statistic over here is much different, we would say significantly different from the hypothesized parameter, then HO is probably not true. So back here we would say, well, is that 1.7 significantly higher than 1.6? And if our calculations show that it is, then we would reject the null hypothesis in favor of the alternative and conclude that HO, the null hypothesis, is probably not true. In our case with the nicotine, we would say that the manufacturer is probably not meeting the standard. So the other possibility here is that there's not enough evidence to convict the defendant, and therefore the person is free. It's important to note here that in a court case, the judge never says that the person is innocent. The judge says that the person is not guilty. In a statistical case, then, if the sample statistic is not too different from the hypothesized parameter, then HO cannot be disproved. And so what we say here then is that we cannot reject HO. Okay? Up here, if we conclude that there's enough evidence, then we would say we reject HO. But if there's not enough evidence, then we cannot or do not reject HO. So you never accept HA. What you do is you're always talking about whether you reject HO or not reject HO. How's the hypothesis test done? Well, what you do is you set up your hypotheses. So in this particular case, the standard is that the manufacturer has no more than 1.6 milligrams of nicotine on average in the cigarettes. The alternative is that it's greater than 1.6. And so we have to make sure that there's enough evidence, really overwhelming evidence, to say that they're not meeting the claim. Why do you need a lot of evidence? Well, because it's costly, and because if the government organization comes in and makes a wrong conclusion here, then there's the reputation of the company at stake there. It's a costly thing to the company. It could end up being a costly thing, of course, to the government in terms of their testing agency. And so you want to make sure that you're making the right conclusion. So you want to make sure that the sample says that beyond a reasonable doubt here. Now, in the case of a court case, you would say we want to be almost certain. In the case of a business case, then usually we want to be, say, 95% certain. So that leaves us with a 5% level of significance. That's the same alpha that we had back in confidence intervals. We'll get to that a little bit more. So the steps that we go through here is, which we're going to formalize actually in a bit here, is I want to go back to that picture that I drew here. So the distribution of sample means, according to the central limit theorem, looks like this. 1.6. And then we get a hypothesized value, an x bar value of 1.7, and the question is, that's significantly different. The way that we do that is we measure this area here. If that area is small, then that means the 1.7 is way in the tail, the upper tail here, and so we would reject the null hypothesis, say there is enough evidence to reject the null hypothesis in favor of the alternative. So a sample is taken, giving us a sample mean of 1.7. If the sample mean of 1.7 is much higher than the mu of 1.6, then it will be in the upper tail of the distribution. So what we do is we find that probability. What's the probability that x bar is greater than 1.7? If this probability or area is small, let's say less than 5%, which is a common alpha value, so we want to be 95% certain of our results, and that means that we got to be okay with a 5% level of significance, then we reject HO in favor of HA. So let's actually work through this problem here, and then we're going to formalize the steps in the next video. So what we have in this particular case then, let's see what we have. X is, let's go back to the problem here. Manufacturer of a certain brand of cigarettes claims that each cigarette contains on average no more than 1 milligrams of nicotine, yada yada. It has a hypothesized mean of 1.6. There's no sigma, so we have to use the S. And we have, it doesn't say anything about normality here. So what we've got then is X is, well, we don't know how it's distributed. We don't know that it's normal. We've got a hypothesized mean of 1.6. The little naught there says that it's hypothesized in the null hypothesis. And then we don't know what sigma is, right? So that's going to mean that we're going to be using a t distribution. Like that. Let's do the calculation here. So we're going to find what's the probability of getting an x bar greater than 1.7. Just to put down over here what we found out, n was 144, x bar was 1.7, and s was equal to 5, I think it was. Need to go back here. Oh, 0.05. Yeah, of course. S is equal to 0.05. There we go. So here's the distribution of sample means. 1.6. We're looking for this area here. We're going to standardize this. In the next one, we're going to go through the flow chart formally and show you the steps here. But remember, we didn't know what sigma was, so we're going to be using a t. So t star is equal to x bar minus the hypothesized mu, so that's the mu naught value, the one that appears in the null hypothesis, over S divided by the square root of n. 1.7 minus 1.6, 2.4. So let's take a look now at a t-distribution. Centered on 0, 143 degrees of freedom, and find out where does 2.4 fall. Right there. And so we're going to look that up on a t-table. Actually, while we're here, let's take a look at what we've got here, which formulae we use here. So was the population normal? Didn't say so. So we come down here. Is n at least 30? Yeah, it was 144. So we go up here. And is sigma known? No. So we have to use S, and that means we use a t-distribution. So we come down here. Is capital N known? No, it didn't say anything about the population. So that means that we're using formula number 3, which is right here. So let's take a look at 143 degrees of freedom down here. Notice that the last one that we have here is 120 degrees of freedom. So we're going to go to this last one, which is, these are actually just Z values. And we're going to come up with 2.40. So we're going to come across here until we find 2.40. And it's right in here, 2.40. So if we go to the top here, we'll find that that's something between 0.5% and 1%. And so this area in here then is something between 0.5% and 1%. And that, of course, is the original probability that we're looking for. Probability of getting an X bar of 1.7. So it's somewhere between 0.005 and 0.01. What does that mean? Here's the important part. The interpretation down here is that there is less than a 1% chance of observing a sample mean of 1.7 if the manufacturer's claim is true. That is, if HO is true. So we reject HO in favor of HA and conclude that the average amount of nicotine in all of the cigarettes is probably higher than 1.6. So in other words, there's enough evidence to say that they're not meeting the standard. So slap them with a big fine. There's a statement at the very end here that says, notice though, that there's still a 1% chance of observing a sample mean this high, even if the true mean is 1.6 or less, as hypothesized. Could have been just by sheer dumb luck that our particular sample of 144 cigarettes had just a lot of cigarettes with more than usual amount of nicotine in there. So we ended up with a high sample mean of 1.7. So due to sampling error then, there's a 1% chance of making the wrong conclusion. And we're going to talk about that a little bit more in this next area, this next section.